What is the main motivation behind the development of Think and Execute framework?
The main motivation behind the development of the Think and Execute framework is to enhance the reasoning capabilities of large language models, LLMs, by discovering a common logic that reflects the shared reasoning pattern behind a given task and applying it to each instance. The framework aims to address the limitations of prior approaches that either perform step-by-step reasoning on the fly without planning or rely on generating a plan described in natural language based on a single instance, hindering the analysis of core reasoning patterns shared across similar instances within a task. By introducing Think and Execute, LLMs are guided to think about common reasoning patterns, translate the logic into a pseudocode format for flexibility, and simulate the execution of the task-level pseudocode to predict the output result. This approach allows for a more efficient and effective way of reasoning by tailoring the logic to each instance, leading to notable improvements over challenging baselines in algorithmic reasoning tasks.
How does Think and Execute differ from prior works in enhancing reasoning capabilities of LLMs?
Think and Execute differs from prior works in enhancing reasoning capabilities of LLMs by introducing a novel approach that focuses on discovering a common logic shared across instances of a task and tailoring it into pseudocode prompts for each instance. This is in contrast to prior works that either perform step-by-step reasoning on the fly without a dedicated planning phase or rely on generating plans in natural language based on observing single instances. Think and Execute stands out by utilizing pseudocode to describe the underlying logic of a task, which allows for more flexibility in applying the logic to each instance compared to natural language or instance-specific code generation. Additionally, Think and Execute involves three distinctive steps. Think, where an LLM identifies common reasoning patterns, generating a pseudocode prompt based on the identified logic, and Execute, where the LLM simulates the execution of the task-level pseudocode to predict the output result. This comprehensive approach enables LLMs to improve their reasoning capabilities by understanding and applying a shared reasoning pattern across instances, leading to notable performance gains over existing baselines in algorithmic reasoning tasks.
Can you explain the three distinctive steps of Think and Execute framework in detail?
The Think and Execute framework consists of three distinctive steps. Firstly, in the Think step, an instructor LM is tasked with discovering the common reasoning patterns of a given task by providing it with a few example questions. The instructor LM then translates the natural language description of the logic into a pseudocode format. This pseudocode format allows for more flexibility in applying the logic to each instance compared to using a programming language like Python. Secondly, in the Execute step, a reasoner LM simulates the execution of the task-level pseudocode to follow the logic within it and predicts the output result of the pseudocode. The reasoner LM is instructed to not only predict the final output result of the code, but also the intermediate execution outputs as rationales. This step aims to maximize the reasoning abilities of the LM by explicitly generating intermediate reasoning steps, known as chain-of-thought reasoning. Lastly, through extensive experiments on algorithmic reasoning tasks, the framework demonstrates the effectiveness of Think and Execute over challenging baselines. The framework's superior performance suggests that discovering the common logic for a given task and applying it to each instance is more beneficial than writing instance-specific code for every instance. Additionally, the framework shows that simulating the execution of pseudocode improves LLM's reasoning more than planning with natural language instructions, even though they are trained to follow natural language instructions.
What are the key components of the meta prompt used in Think and Execute?
The key components of the meta prompt used in Think and Execute include providing demonstrations of other tasks, 3 example questions, analysis and P for each task from T, as well as the target task T, 3 example questions without the answers. This meta prompt serves as a guide for the instructor LM I to generate a task-level pseudocode for the given target task T. The meta prompt is crucial in helping I. Discover the underlying logic for solving the task and constructing a prompt describing the logic that will be applied to all instances of the task during the execute phase. The meta prompt aids in focusing I. on the shared reasoning process among all instances, which is essential for creating a task-level prompt that can be effectively applied to each instance.
How does the instructor LM generate the analysis in think and execute?
The instructor LM generates the analysis in think and execute by first constructing a meta prompt that includes demonstrations of other tasks related to the target task. Then the instructor LM analyzes the target task based on the meta prompt to identify key reasoning logic required to solve the task, focusing on the shared reasoning process among all instances. After the analysis, the instructor LM writes a prompt in the form of pseudocode that breaks down the necessary reasoning steps for solving the target task. This pseudocode prompt is designed to efficiently describe the logic behind the task and guide the reasoner LM in executing the logic for a given instance. The pseudocode format is chosen over natural language for its effectiveness in describing the task logic and providing guidance on generating rationales during the execution of the code. The analysis and pseudocode prompt generation steps are crucial in think and execute as they help in discovering the common logic for a task and tailoring it to each instance to enhance the reasoning capabilities of the language models.
What is the significance of using pseudocode format over natural language in think and execute?
The significance of using pseudocode format over natural language in think and execute lies in its efficiency in describing the logic behind a task and guiding the LM to apply the logic to each instance effectively. Pseudocode allows for a more concise and structured representation of the underlying reasoning steps needed to solve a given task. It helps in avoiding repetitive instructions and provides clear guidance on what and when to generate rationales during the execution process. The pseudocode prompts in think and execute enable the reasoner LM to track the state of variables and generate intermediate reasoning steps accurately, leading to improved reasoning abilities. Additionally, pseudocode format facilitates the transferability of the discovered logic to smaller LMs, enhancing their reasoning capabilities as well. The use of pseudocode prompts in think and execute has shown to outperform natural language planning approaches, indicating that pseudocode is more effective in conveying the necessary logic for solving tasks and benefiting LLM's algorithmic reasoning across various tasks.
How does the reasoner LM simulate the execution of the task-level pseudocode in think and execute?
In think and execute, the reasoner LM simulates the execution of the task-level pseudocode by tailoring the logic in the pseudocode for the given instance. The reasoner LM is instructed to predict not only the final output result of the code, but also the intermediate execution outputs as rationales. It predicts a list of outputs by simulating the execution process of the pseudocode, where each output denotes the system output from print statements. These intermediate execution outputs serve as rationales towards the final answer. The reasoner LM is guided to generate the expected outputs from all print functions in the code, mimicking the behavior of a compiler. The final answer for a given question is outputted with a specific command as the last system output. This approach aims to maximize the reasoning abilities of the LM by explicitly generating intermediate reasoning steps and tracking the state of variables as they change during the execution of the code.
What are the algorithmic reasoning tasks evaluated in the experimental setup of the paper?
The algorithmic reasoning tasks evaluated in the experimental setup of the paper are Dyke languages, geometric shapes, navigate, reasoning about colored objects, temporal sequence, tracking shuffled objectives, and web of lies.
How does think and execute compare with direct prompting and zero-shot caught in terms of performance?
Think and execute outperforms direct prompting and zero-shot caught in terms of performance. Specifically, think and execute shows significant improvements over both direct prompting and zero-shot caught regardless of the model sizes used. The framework achieves notable enhancements in reasoning capabilities compared to these baselines, indicating that explicitly generating a plan with pseudocode is more effective in improving the logical reasoning abilities of language models, LLMs, than simply encouraging LLMs to generate intermediate reasoning steps on the fly. In experiments conducted on algorithmic reasoning tasks from Big Bench Hard, Think and Execute consistently outperforms direct prompting and zero-shot caught, showcasing the effectiveness of the approach in enhancing LLM's reasoning capabilities.
What are the advantages of using task-level pseudocode prompts over instance-specific Python code prompts according to the paper?
The advantages of using task-level pseudocode prompts over instance-specific Python code prompts, as outlined in the paper, include the ability to apply a common logic structure to all instances of a task, leading to improved reasoning capabilities in a wider range of algorithmic tasks. The task-level pseudocode prompts benefit LLMs by providing a shared reasoning pattern that can be tailored to each instance, enhancing reasoning efficiency and generalizability across tasks. Additionally, the pseudocode format allows for more flexibility in describing the logic behind a task, avoiding repetitive instructions and guiding the generation of rationales at specific points during code execution. The pseudocode prompts help LLMs track the state of variables and understand the logic behind the task more effectively than instance-specific Python code prompts. Furthermore, the pseudocode prompts generated by LLMs can be transferred to smaller LLMs, boosting their reasoning abilities, showcasing the efficiency and scalability of the task-level pseudocode approach. Overall, the paper demonstrates that task-level pseudocode prompts outperform instance-specific Python code prompts in all tasks, highlighting the effectiveness of using pseudocode to express and apply the necessary logic for solving algorithmic reasoning tasks.